So our first speaker today is going to be Dale Kocevski. For some reason, it didn't come out smooth. From Colby College of Maine, and he's going to tell us about little red dots.
All right, thank you. Good morning, everyone. Indeed, I'm Dale Kocevski. I'm a professor at Colby College up in Maine, and I'll be talking about this enigmatic population of sources that JWST has uncovered that have been dubbed little red dots, and what we think we understand about them, what we know about them, and then what Roman will help us tease out about their nature, especially at lower redshifts. So Steve did a great job introducing some of the surprising results that came out of JWST in the first cycle. And I just wanted to touch on one of the three topics that Steve mentioned, and that is these potentially overmassive galaxies in the early universe. So pretty quickly, folks noticed in the NIRCam imaging that you had these sources that are relatively red, relatively bright, and pretty common. There are several of them in each NIRCam pointing, and based on their SED fit stellar masses, they had masses on the order of 10 to the 10 solar masses. And they were being found at redshifts of 7 or so. So we're talking 700 million years after the Big Bang. And so these are two sources from Ivo Loewe's 2023 paper. These things look like they have, let me go back. These things look like they have double breaks. There's a Lyman break there and a Balmer break, so it looks like these things are at high redshift, and they look like evolved stellar populations at high redshift. And so right away, folks started pointing out that there really isn't enough time for that much stellar mass to build up. It requires too many baryons. It would basically require all the available baryons in the halos of these systems to form into stars at these redshifts. And so right away, there were problems with these really massive galaxies early on, and the press picked up on this and immediately started calling these things universe-breaking galaxies, because one solution to these things is that the universe is simply older than we estimated, and so we had a longer amount of time to build these massive galaxies early on. And so these things were referred to as universe-breaking galaxies and the such. We were fortunate enough in Sears to get the first spectroscopic follow-up of a couple of these sources, and this is one of them here. It's a Sears 746. As you can see, it's this compact little red object here, and it basically has this broadened H-alpha line. So we've got a line width here of about 1,800 kilometers per second, translates to a black hole mass of about 10 to the 7 solar masses. When we look at the forbidden lines in this source, like the oxygen 3, we don't see similar broadening. So we don't think this is just due to star formation-driven outflow in these systems, but instead we think it's basically gas that's orbiting around a supermassive black hole, giving us this Doppler broadening. This is one such source. There's a second one. Again, if you squint, you can see this H-alpha. You get this really faint broad line, right? So these don't look like quasars where the lines have these crazy broad lines, but they're faint and they're ubiquitous in the Balmer lines of these sources. And again, pretty compact red object there. If you look at the bolometric luminosity and the black hole mass of these sources, they're, like I said, very different than the traditional quasars that we had come to know at high redshift. So this is basically black hole mass versus bolometric luminosity. Redshift 4 to 7 quasars are sitting up here at black hole masses of 10 to the 9 or so. Local AGN sitting here at black hole mass of 10 to the 6. And these sources, the two sources that we identified, fit basically closer to the local AGN population than the bright quasars we knew about before JWST. So we were basically able to start probing black holes that are more representative of the normal black hole population as opposed to the quasars, which are these kind of extreme outliers at high redshift. And so pretty quickly after we put out that result, within a few months, several teams started reporting a large fraction of these faint broadline sources. So these are compilations from Ichi Hirkani, Yurat Methi, and Roberto Maiolino. Here's another compilation that we put out led by Anthony Taylor. So this is a compilation of broadline sources from Sears and Ruby's data set. And essentially, these things are really quite common. You go out there and you take a spectrum of bright sources, and there's a good bet you're going to find a broad emission line in the Balmer lines. But what I want to focus on today is a subset of these broadline sources that have these really unusual V-shaped SEDs in red colors. These are the so-called LRDs. About 20 to 30%, that fraction is actually slowly creeping up. It could be as high as 40% of the broadline sources identified by JWST at high redshifts have these really red colors and have been dubbed little red dots. And little red dots have a very unusual spectral energy distribution. They basically are extremely red in the rest frame optical, so they have this steep continuum slope in the rest frame optical, and then they have what appears to be a UV excess at short wavelengths. So they're relatively blue in the UV and they're relatively red in the optical. Most dust attenuation laws don't work that way. If you're red in the rest frame optical, you're going to be red in the UV as well. And so right away, this told us that there might be multiple emission mechanisms going on with these sources. And so we speculated in that first paper that either we're looking at a massive galaxy, so a galaxy that has a mass of 10 to the 10, 10 to the 11 solar masses, and then we're looking at AGN light coming out in the blue, or we're potentially looking at a heavily dust-obscured AGN, and then the blue light is coming from a low-mass host. And so this combination of this explanation of the SCDs has been debated in the last 3 years about these things, but essentially these are the two prevailing theories at the time, and we kind of concluded that we were looking at a dust-obscured AGN, and I'll come back to why that's actually not correct a little bit later. But the real issue, the real problem with the massive galaxy scenario is that the size of these things is actually constrained to be really, really small. So the best estimate we have to the size of the LRD comes from this triply lensed LRD that Lucas Furtak identified in Abel 2744, and based on the shearing effect, if there's because of the shearing effect of the gravitational lensing, if there's any extended component, you basically see that sheared out, and you'd actually be able to resolve out that extended component. And so Lucas basically estimated that the size of this thing, that it had a constraint of about 35 parsecs on the size. And so it's really hard to fit 10 to the 10 solar masses of stars inside 35 parsecs, right? And so this would make the LRDs the most, the densest objects we've identified in the universe. They'd basically be sitting up here with stellar densities that far exceed the nuclear star cluster that's found in the Milky Way, for example. And so it's pretty hard to explain their red optical colors with a massive galaxy just based on the stellar densities that are implied. As Steve mentioned yesterday, we actually did a photometric census of LRDs. After identifying them spectroscopically, we went into the JWST legacy fields and tried to look for sources that had that V-shaped SCD, that red optical and blue UV slope. We did this using a bunch of different pass bands so that we could basically probe these things as a function of redshift. Here's a couple of examples of these sources at redshifts 4, 6, and 8. Basically, they're compact, and they all have this V-shaped SCD, and so we're selecting them this way. And so we found a sample of about 350 of these LRDs in several of the JWST legacy fields. And one of the things that comes out when you select them photometrically like this is that you realize that they do seem to be a uniquely high redshift phenomena. So essentially, the redshift distribution is such that their number density starts to rise at around redshift of 4, they plateau, and then we think this drop off at high redshift is basically just incompleteness. As the rest frame optical pushes past the near cam sensitivity, we basically lose the ability to see that rising slope. But at low redshifts, we should easily be able to detect them at redshifts 2 to 4, and we find that the number densities really plummet at those low redshifts. Now, this has been confirmed with ground-based imaging. So this is a result from a model where they used Subaru as a prime cam imaging, and they found that number density drops off. Now, this is not to say that LRDs don't exist at low redshift. It's just that their number densities appear to be dropping. And so, of course, you guys probably see where I'm going with this. We need large areas to be able to identify them at lower redshifts and figure out what the LRDs are becoming at lower redshifts. And I'll come back to this later in the talk. Now, if you select these things photometrically and you then follow them up spectroscopically, one of the things we found is that they almost always have broad emission lines. So Jenny Green was the first to show this with the uncovered prism data. She found that 2/3 of the reddest LRDs have broad lines when you select them to have this V-shaped SED. We did a similar study using Sears and the Ruby's data set and estimated that about 80% of our photometrically selected LRDs have broad emission lines with widths ranging from about 1,000 to 4,000 kilometers per second. And then the Ruby's team themselves went a step further and simply said that all point sources with these V-shaped SEDs basically have broad lines. And so this, I think, is really telling because it tells us that the presence of a black hole at the center of these things is somehow impacting the colors of the sources, right? So we're selecting them to have unique colors, and those colors are almost always associated with with these broad lines. And so that's something that we see typically in quasars. Quasars alter the color of the source. So you can pick out quasars photometrically because they have strange colors that deviate from galaxy colors. And then you always find broad lines. And so we find a similar thing in these sources that are substantially fainter than quasars. Now, one of the reasons why folks are interested in LEDs, other than the fact that they're just, they're unique and we hadn't seen them before, is that they're actually quite common. They're not outliers. If you look at their UV luminosity function, again, this is based on photometrically selected sources, LRDs. This is the UV luminosity function at redshift 5 and at redshift 7. The LRDs are in red here. So this is from our LRD census paper from last year. And what we find is that the number density of LRDs is substantially higher than that of quasars, and so we're talking about orders of magnitude higher than bright quasars identified from the ground. But they're also higher, the number density is also higher than your canonical AGN at these epochs, right? So X-ray AGN, UV selected AGN. The LRDs are basically, if they are a new population of AGN, they seem to be much more ubiquitous than the traditional AGN that we've come to know at lower redshifts. And so they actually become the dominant accretion mechanism onto these low mass black holes at the early times. So again, if you take a near-cam image with JWC, you are going to have half a dozen LRDs in one of those images. They're basically that ubiquitous. One of the things that we're really interested in is understanding what types of galaxies, if any, that these things are living inside. And I said already that many LRDs basically look point-like with no extended emission. But as you move to lower redshifts, we do actually start to see hosts that we can resolve. And so this is an example of an LRD at redshift 3.1 where, I don't know if the contrast is doing this justice, but you can see this, move back, wrong button. You can see that central point source. If we subtract off that central point source, you can see a slight extended emission coming from a host galaxy here. And it turns out if you do this type of surface brightness modeling and estimate what the flux is for that extended host, it agrees really well with a scenario where the rest UV is coming from a galaxy, and the rest optical comes from that reddened AGN. And so in certain LRDs, we can actually resolve this out, and we can verify that the UV is coming from the host. In other sources, these things are completely point-like, and we don't see any sign of the host, but we do see that same SED shape. And so we can basically just assume that that rest frame UV is coming from the host galaxy. And so this allows us to at least get an estimate of what the mass of these host galaxies are. And so this allows us to put these sources on a black hole stellar mass relationship. This is, again, black hole mass, stellar mass on the x-axis, black hole mass on the y-axis. What's plotted here, there's a lot going on here, but this is essentially these orange points here are local broadline AGN. And so essentially, local broadline AGN have certain black hole to stellar mass ratios where they essentially sit down here. This gray line is the local scale relationship from Cormody and Ho. It's essentially just the relationship between the stellar mass of the host galaxy and the black hole mass. And what we find is for our sources, both LRDs and non-LRDs, so essentially just the broad line sources that JWC is identifying, is that these things scatter substantially above the local relationship. They appear to have elevated black hole to stellar mass ratios. The black holes are more massive for a given host mass at these early times, which seems to favor an overmassive black hole scenario. That essentially, the black holes are growing first and the galaxies are following afterwards. We don't yet know how these things evolve onto, if they evolve onto the local relationship at lower redshifts. This is one of the reasons why we might want to follow these things at lower redshifts and see what's happening. Do LRDs at redshifts 2 essentially sit closer to this relationship? But this seems to favor an overmassive black hole scenario. And of course, we want to study this because we want to understand something about how the seed population of these black holes formed. We still don't know whether the seeds of these black holes formed via just stellar processes where you have stellar mass black holes that then grow at exceedingly high rates to reach the high masses that we see at high redshifts, or whether you start with an overmassive black hole and you essentially then just have to fuel that thing at a pretty benign rate to get the black hole masses that we see. And this seems to tell us that we have overmassive black holes really common in the early universe. We did do a statistical study to determine whether this was really just a selection effect or whether we were actually seeing a true evolution in the scaling relationship. And when we essentially factor in our selection biases, we find that this offset, our best fit scaling relationship, is still greater than a 3 sigma deviation from that local relationship shown in blue here. So it does look like the black holes that we're finding with JWST appear to be overmassive relative to their host, relative to their low redshift counterparts. Now, there's been a lot of debate in the literature as to whether the black hole masses that we're measuring for LRDs is actually correct, and I think this is very much an open question. We don't yet know because we're basically using local scaling relationships to derive the black hole masses for these things based on the width of the lines and the luminosity of the lines. We don't have reverberation mapping results, direct measurements of black hole masses in the early universe to check this. But the single source where we think we have a dynamical direct measurement of a black hole mass of an LRD at redshift 7 does seem to corroborate that the black hole mass is overmassive relative to the host galaxy. This is a great result from the JADES team, where they used IFU observations that basically pick out this offset velocity, and they could basically see that they've got this Keplerian rotation curve that allows them to derive the direct black hole mass measurement. And if you plot this up on a stellar mass, black hole mass plot, this source sits way up here. Local AGN sit down here. This thing basically, this is the black hole mass stellar mass ratio of 1. Right, and so this thing sits above this line. The black hole appears to be more massive than the host galaxy, which is, really, really bonkers. So these things look unusual. They look different than our local AGN. And so this begs the question: are these things really powered by AGN? And this is one of the big debates that's been happening for the last 3 years. Do we really see? Do we really think these are powered by your traditional AGN that we know at lower redshifts, or some variation of it? And there's lots of reasons to basically question whether these things really are powered by AGN, by an active galactic nucleus. And one is that these things are really red, and so they should have lots of dust. But in fact, when you look at their SEDs at long wavelengths with the MIRI instrument in JWST, you see that this thing basically flattens over as opposed to rising. And so that this rising continuum would be reprocessed dust emission, right? So that dust is going to absorb some of that AGN light, reprocess it at longer wavelengths, and we basically don't see that. And so the question is, where's the dust? Where's the dust that's making these things look red, right? Another thing that is unusual about these is that they are X-ray weak. They deviate from local optical to X-ray relationships by greater than 5 sigma. You can stack as many LRDs as you want, and you basically don't find any signatures of X-ray emission coming from them. And then several LRDs, as Steve mentioned yesterday, appear to have stellar breaks in them. This seemed to be a game changer. This kind of killed the idea that we were looking at light coming from the accretion disk of the black hole. Instead, it looked like we were just looking at an evolved stellar population in these sources. So these are two sources from Josephine Baggins' paper where you can see this break at the Balmer limit, and it looks like basically an evolved stellar population, or basically like a stellar atmosphere. I think the breakthrough in understanding what was going on with the LRDs is that we noted that the several of these sources that have these break features also show absorption lines in their Balmer lines. This was something that Urat Methi noted in his original LRD paper, and we noted in our census paper that a high fraction, 25% of our sources, showed these strong Balmer absorption features, as well as absorption in helium-1, for example. And so soon after this, Roberto Mailino and Kohi Iniyoshi proposed this model where if you basically surround a black hole with really dense gas envelope, you can basically reproduce these absorption features. So essentially, you'll end up getting trapping inside this really dense gas that basically eats away at the emission profile. But what's interesting is that the same gas that produces these absorption features also produces a break that looks like a stellar break, but is in fact just due to gas basically absorbing light at the Balmer limit. And so this basically led us to this idea that these things are not in fact dust obscured, but instead just enshrouded with so much gas that basically that gas is reddened just by attenuation, not because of dust scattering. So this model was actually beautifully validated with the detection of a handful of sources that I always call extreme LRDs, but I feel like we missed a chance to coin XLRD, but nobody calls them extreme LRDs. But they look like extreme LRDs in the sense that they have extreme breaks. This is an LRD that Rohan and I detected at redshift 7. It's basically got this rapid increase at the Balmer limit. It basically looks like almost like a thermal spectrum. This is another source that Anna de Graaf identified. It's called the Cliff. It's also got this crazy crazy break at the Balmer limit. And so what's interesting about these sources is that the break strength far exceeds the break strength that you would get from a stellar break. So these things, if this is the Balmer break strength, these things sit up here, and essentially the maximum stellar break that you would expect is somewhere down here. And so these things basically told us that, in fact, we were looking at gas-enshrouded black holes and not an evolved stellar population in this thing. We identified a similar source at a redshift of 9. So Steve mentioned this yesterday. This is a paper led by Anthony Taylor using the Capers data. We identified a source that has this break. Again, this thing is at a redshift of 9.3, is the highest redshift LRD detected. In this case, we've got a nice broad H-beta line, so sitting over here. And from that H-beta line, we could derive a black hole mass. In this case, unlike Rohan and Anna's sources, this source actually has a UV excess, which we attribute to the host galaxy. So we can derive a host mass. And when we put this thing up on a black hole, we plot up the black hole to stellar mass ratio, which is up here, at a redshift of 9, this thing looks really quite elevated. If this is the local relationship, this thing looks like it has an extremely elevated black hole to stellar mass ratio. And this is interesting because at these high redshifts, now we're starting to get to the point where we can start placing constraints on seed masses. So essentially, this thing would either have to be formed by a heavy seed, so essentially like a direct collapse black hole that forms a black hole with a mass of 10 to the 4 solar masses, and it grows via Eddington accretion. Or it basically, if it's a light seed, if it basically came from a supermassive star that collapses and leads to a light seed with a mass of 10 to the 2 solar masses, this thing would have to grow experience a sustained super Eddington growth over its entire lifetime to reach the mass ratio that we're seeing at a redshift of 9.3 or so. So this really starts to tell us that perhaps we're looking at, this is telling us something about the initial seed formation, that we're looking at overmassive black holes that may be directly collapsing into massive seeds. So this is the picture now that we have of these LRDs, are these gas-enshrouded black holes, infant black holes in the early universe. And let me jump, get my there we go. So the prevailing theory now is that we're looking at infant black holes in their first episodes of accretion. And so how exactly that comes about is still a matter of debate. We had a paper out led by Fabio Picucci earlier this year where we proposed that perhaps we were just looking at a direct collapse model where we've got this gas cocoon that's falling into the black hole, and it's basically being supported, and it's basically providing that cocoon around that black hole. And that we showed basically with modeling that you could reproduce many of the spectral features of the LRD just based on this direct collapse model. Kohei and Yoshi proposed that perhaps regardless of how the black hole forms, it could just be that LRDs are the first 1 or 2 accretion episodes onto newly formed seeds. And so in this case, this is his model showing basically if you just assume that the first 1 or 2 accretion episodes onto a newly formed black hole, regardless of how it forms, is an LRD, then the number density that you predict basically drops off just exactly as you see with the number density of LRDs. And then eventually these things transition into normal X-ray AGN, which is shown in green, and the normal AGN population that emerges from this LRD thing. But the key here is that almost all of these models trying to explain what LRDs are basically have the LRD number density plummeting at low redshifts. But in fact, there was a recent result by the Euclid team that basically argued that the number density for these things at low redshifts is actually higher than we've been estimating. So this is the Euclid estimate up here, almost an order of magnitude larger than the model result from using Subaru HyperSprime imaging. And so this is, of course, the exactly what Roman can help us with, right? At redshifts of 1 to 2, Roman will easily be able to pick up these V-shaped SEDs, and it's going to have the spatial resolution needed to pick out the compact morphologies. One of the criticisms of this result is that Euclid might just not have the resolution to determine whether these things really are compact or whether you're just picking up the rise of passive galaxies at redshifts 1 and 2, right? So the high latitude wide area survey is going to be great for this, and in particular, as Steve mentioned yesterday, the deep tier is going to be key because it will cover 19 square degrees in 6 filters, and those 6 filters are exactly what you need to basically be able to shape, to measure out the V shape that LRDs have. And so this is going to be 40 times larger than the JWC legacy ski fields. And so just based on that area and based on our 2 estimates from ground-based imaging and from Euclid, we can estimate that we're going to get somewhere between 1,000 to 10,000 LRDs. And so we're going to pretty easily be able to figure out exactly what's going on here and whether the number density is dropping at low redshifts, and then what the LRDs are becoming. Are they growing galaxies around them? Do they disappear completely? And so the other last point that I'll make is that this business of the stellar masses of the LRDs still is really unresolved because we're assuming this based on just our SED modeling of these sources. We often don't have direct measurements of the galaxy masses. But of course, one of the things that Roman will do for us is provide clustering measurements. And so, as Steve mentioned yesterday, we're going to have a fantastic ability to measure the halo masses of these sources. This has been used really well with quasars, and are going to basically be able to do this with LRDs with a much larger sample, a much larger continuous area to basically figure out what the halo masses of the host galaxies are here and determine whether they really do live in these low mass galaxies and they are as overmassive as we think they are. So maybe with that, I think I'm out of time, and so I'll just throw up my summary slide and take any questions you guys might have. Thanks.
Questions?
Hi, Dale. Thanks for the really great overview. Just a quick question about your they're not supermassive, black hole to stellar mass relation.
Yeah.
How, you go back to your figure.
Sure.
I think those uncertainties are aspirational. How confident are you?
Yeah, so there's uncertainties in both axes here, right? So our stellar masses are coming from the SED fitting. I think I'm pretty solid on the SED fitting because we have examples where you can see the extended host galaxy that fits with the SED fit. And so I'm pretty confident about the stellar masses. The black hole masses, it's anyone's guess as to whether the local scalar relationships are holding. I will say that the Gravity Plus team has done some direct measurements at redshifts 3. They found that the local scaling relationships for the single epic black hole mass scaling relationships are off by maybe a factor of 3 or so, but we would need a factor of 10 to 100. Our scaling relationships would have to be off by quite a bit in order to bring all those sources down. And so I'm not confident that these black hole masses are spot on, but I don't think we're off by like 2 orders of magnitude, which is really what we would need to bring these down to the local relationship. So I'd say, tentatively, the handful of direct measurements we have say the black hole masses are not that off, but there are others that argue that the broadening that we're seeing is due to electron scattering, and it has nothing to do with virial motions, and so that could mean that the black hole masses are completely off if that's the case.
Dale, I'm not so worried about the black hole mass. I'm interested in the host galaxy measurements because you had said that at the lower redshifts you do have examples where you're actually measuring the host. Now the masses of those are going to be uncertain too, but are you saying that those are fundamentally different objects than what you're seeing at redshifts 7
No,
where you don't see anything, or the host has just had time to grow, or are they 2 different populations?
Yeah, it's a good question. I don't know whether it could be the case where the host has had time to grow. It could be that it could be that we're looking at something different. Or, in the direct collapse model that Fabio Cucci proposed, the direct collapse model then sinks into a galaxy at later times, and so then you end up having it. So the host hasn't actually grown, but it basically merges into the halo that provided the Lyman-Werner radiation to produce the black hole. So, it's not really clear what's going on at lower redshifts. But the thing that's interesting is that I find interesting about this is that you've got this distinctive SED, and like I said, you could basically you could reproduce this SED just with our Galfit modeling, and then you go in and you say, well, this source, when I do a Galfit model for this source, I see this is at higher redshift, this is at redshift 5, I see no host, but the SED looks identical, right? And so then I'm just basically, following that same approach. Yeah.
How many, that's an example. How many can you actually make?
Oh, at low redshift, probably, there's probably a dozen or so where we can actually resolve out the host and see what's going on. And almost universally, it's the case where the host appears at the UV side, and then the thing dominates at the redshift, at the red advance.
Yeah, thanks. Good stuff. I guess just kind of following up with that, is that kind of some selection effect, though, that you're not able to see the host kind of by definition?
Yeah, we're selecting out things that are compact. Yeah, that's a good point. I will say, in this source, when you measure the effective radius of this thing, it's still pretty small. So in our photometric census, you're right, we have selected things that were within a factor of 1.5 times the stellar locus. So essentially we find this where the stars live, and we say something has an effective radius 1.5 times greater than that, we basically call it compact. And in cases like this, the effective radius is, there's so much light coming from that central point source. Yeah, you could see there's, you're 2 orders of magnitude below where you are at the reddest bands. So the effective radius is really driven by the central point source. So it doesn't affect the size estimate too much. But you could potentially bias yourself from finding things that have a red point source and a really extended object around it.
All right, we should probably move on. Let's thank the speaker one more time.